You know how we're always told that sharing is caring? Well, today we're going to flip that on its head and explore why, in the world of computers, sharing work equally can actually be the slowest way to get things done. It's a pretty wild idea that powers so much of our digital lives, but it's totally counterintuitive. I mean, we've all been there, right? You're at the grocery store, you pick what looks like a good checkout line, and somehow it just grinds to a halt. You peek over, and the other lines are just zipping by. That exact feeling, that bottleneck frustration, that's really the heart of what we're digging into today.
So let's take that checkout line feeling and apply it to a workplace. Okay, picture a manager. They split a huge stack of paperwork into 3 equal piles for 3 employees. Seems fair, doesn't it? But what if one employee is a total speed demon and another one is, let's say, a bit more methodical? The whole project gets held up just waiting on that one person to finish their fair share. Now, look at the smart way. You give the fastest worker the biggest pile, and what happens? Everyone finishes at about the same time, and the whole job gets done way, way faster.
Now, this whole SMART strategy, it has a name, and it's basically the hero of our story today: load balancing. In the tech world, this is the secret sauce. It's the art of intelligently handing out tasks to make sure systems are quick, responsive, and don't just collapse under pressure. It's really the digital version of a brilliant manager who just gets their team's strengths. This quote just nails it. The whole game changes when you stop thinking of resources, whether it's people or computer processors, as all being the same. Instead, you've got to recognize that they have different performance levels, and then use those differences to your advantage. It's such a simple idea, but wow, is it powerful. So, analogies are great and all, but how do we know this really works? Let's shift gears from theory to a real, concrete example from our source material. A simple but super clever computer lab experiment designed to prove this exact point in a head-to-head race. Okay, so in this experiment, we've got a few key players on the field. First up, there's the user interface, or UI. That's our manager, the one calling the shots and handing out the work. Then you have the team, 3 different computer programs, just called worker A, B, and C. Their whole job is to crunch some serious numbers. And finally, how do they talk to each other? They use a simple shared folder, the file system, which acts like a digital message board, where the manager posts jobs and the workers drop off their finished results. Now, here's the twist that makes this so realistic. The experiment deliberately makes the workers different, just like a real team, right? Some are just naturally faster than others. The way the code does this is by adding little artificial delays, a tiny pause during each calculation to act like a slower CPU, and another little pause before submitting the answer to act like a slow network. So how does our digital manager figure all this out? How does it know who its star players are and who's lagging behind? Well, just like any good manager, before you give out the big, important task, you've got to do a little performance review. The manager's strategy is pretty slick. It gives each worker a small, identical test job. Just add up the numbers from 1 to 1,000. Then it times them. This is that small, upfront investment of being smart, a quick little benchmark that's about to pay off big time. From that time, it calculates a performance score called R, which basically means items per millisecond. Simple, right? A higher R score means you've got a faster worker on your hands. And whoa, look at the results from that test. You can see it clear as day on this chart. Worker A is an absolute rock star. Worker C is pretty solid, dependable. And worker B, well, worker B is definitely our slow lane. This is so important. Without this quick test, our manager would be totally flying blind. All right, let's get to the main event. The manager knows each worker's speed, so now it's time for a proper race. We're going to run the exact same massive job twice, but using 2 completely different strategies. This is it, the fair way versus the smart way. So on the left, you've got the even division method. This is our fair but kind of clueless approach. It takes this huge range of numbers and splits it into 3 perfectly equal chunks. 1 for you, 1 for you, 1 for you. On the right, though, is the load balance division. This is our smart method. It uses those R scores we just talked about to divide the work proportionally. Our star, worker A, gets the biggest piece of the pie, worker C gets a medium slice, and our slow and steady worker B, it gets the smallest, most manageable chunk. First up, the fair even division method. The manager splits the work equally, hits the stopwatch, and we wait. And we keep waiting. The final time comes in at 8,452 milliseconds. So why so slow? Because even though our star player, worker A, finished ages ago, the whole process got stuck waiting for worker B to chug through its equally sized, but for it, absolutely massive, portion. And now for round two, the smart load-balanced run. The manager assigns the work based on each worker's proven speed and bam! Look at that result, 5,127 milliseconds. It is so much faster. The magic here is that all three workers finished their custom-sized jobs at almost the exact same second. Nobody was sitting around waiting. Zero time was wasted. The numbers really do speak for themselves. But what's the big takeaway here? Let's break down the verdict and, more importantly, let's talk about why a little experiment like this actually matters a whole lot in our everyday lives. And here it is, the final score. The time difference, the delta, between the two methods is a massive 3,325 milliseconds. That's a performance boost of nearly 40%. And it all came from one simple change, being smarter, not just fairer, about how you assign the work. And this isn't just some fun little lab project. This exact principle is the invisible engine that makes the whole modern internet work. It's the reason your favorite streaming service doesn't buffer. It's sending your request to the server that's least busy. It's how online stores somehow survive the absolute chaos of Black Friday. It's why your social media feed loads in the blink of an eye. The entire cloud is literally built on this idea of intelligently balancing the load. Which, leaves us with one final pretty fascinating question. We've seen how incredibly powerful this is for computers. But what if we started applying this principle everywhere? I mean, imagine traffic lights that could adapt in real time to balance the flow of cars, getting rid of traffic jams. Or hospital systems that could dynamically assign patients to the least busy wings or doctors. The potential for a faster, more efficient, and just plain smarter world is huge. The only question left is, what are we going to balance next?